Welcome to the Explainer. Let's dive right in and crack the ultimate astronomical cold case, the search for the phantom ancestors of literally every single star in the night sky. We are hunting the universe's very first stars.
Picture this: the universe right after the Big Bang. The amount of heavy elements in existence? Exactly zero. The cosmos was just a sea of pristine hydrogen, helium, and a tiny, tiny dash of lithium.
So, if everything started as this pristine, simple gas, we've got a massive mystery on our hands. How did we get the complex building blocks of life? The carbon in our cells, the oxygen we breathe, the iron in our blood. Where did all that actually come from?
Okay, before we introduce our prime suspects, we need to clear up a kind of quirky astronomical definition. To an astronomer, literally any element heavier than hydrogen and helium is called a metal. Yeah, even gases like oxygen and carbon are considered metals here. Basically, the older a star or galaxy is, the fewer of these metals it's going to have.
Section 1. The Suspects, Giants of Cosmic Dawn.
Looking at our cosmic family tree, astronomers split stars into distinct populations. Population 1 stars, like our Sun, well, they're young and packed with metals. Population 2, they're older and metal poor. But population 3 stars, these are the holy grail, the absolute first, pristine generation formed with exactly zero metals.
So how did they actually form? Well, around 100 to 250 million years after the Big Bang, dark matter created these massive gravitational wells called mini-halos. These cosmic potholes allowed that pure, unpolluted hydrogen and helium gas to pool up, cool down, and eventually ignite under absolutely immense pressure.
Here's the catch, though. Because that early gas completely lacked metals, it couldn't cool off efficiently by radiating heat away. And without that cooling effect, the gas clouds just couldn't fragment into smaller pieces like they do today. The result was these monstrous, unfragmented behemoths that were completely unlike our own Sun.
We're talking about a staggering scale here. Theoretical models suggest these primordial leviathans could weigh in at up to 300 times the mass of our Sun. They burned insanely hot, surface temperatures pushing 100,000 Kelvin. They poured out this intense ultraviolet radiation that literally helped reionize the entire early universe.
Section 2. Live fast, leave a beautiful corpse.
But being that massive and luminous is a really dangerous game. Burning that hot comes with a devastating cost to your lifespan. While our Sun is going to live for billions of years, these population 3 giants burned through their nuclear fuel in a cosmic blink of an eye. We're talking just 2.5 to 10 million years before they face some seriously explosive deaths.
And man, those deaths were spectacular. For stars between 140 and 260 solar masses, their lives ended in what's called a pair instability supernova. Basically, inside the core, intense gamma-ray pressure triggered the creation of electron-positron pairs. This caused a sudden, catastrophic drop in internal pressure, the star collapses, and the resulting explosion is so violently huge that it completely unbinds the star. No remnant core left behind whatsoever. Just gone.
Now, for the absolute heaviest stars, the ones tipping the scales over 260 solar masses, the process was completely different. They went through photodisintegration and just collapsed directly into the universe's very first black holes. In fact, these might actually be the initial seeds for those supermassive black holes we see lurking in the centers of galaxies today.
Section 3. Forging the first metals.
These catastrophic explosions weren't just cosmic fireworks. They were, hands down, the most important chemical events in history. Those para-instability supernovae violently dispersed the very first metals, specifically carbon, oxygen, and iron, right into the interstellar medium. By doing that, they completely rewired the chemistry of the universe, setting up the cooling properties of space and providing the exact ingredients needed for the next generation of stars, and ultimately, planets like ours to form.
Section 4. Hunting Cosmic Ghosts.
So if these stars are the ancestors of literally everything, why is finding them the hardest detective work in modern astronomy? Well, it's the perfect storm of hiding spots. First off, the big ones burned out billions of years ago, and as we said, their supernovas left no remnant cores to find. Second, some theories suggest a few smaller, lower-mass population 3 stars might actually still be alive today. But over billions of years, they've likely swept up metallic dust from space, wearing it like a disguise so they just look exactly like normal, later-generation stars.
But recently, we got a massive break in the cold case. Enter the James Webb Space Telescope.
Peering all the way back to the edge of cosmic time, JWST spotted LAP-1b, a galaxy that is actively being born in the early universe. When researchers actually analyzed the light from LAP-1b, they found something mind-blowing. It has a metal concentration of roughly 1/240th of our Sun. That is a record absolute low. It's a huge clue telling us that this galaxy is incredibly pristine and has barely been enriched by any prior stars. Lead author Kimihiko Nakajima perfectly captured the hype of this discovery. He noted that their spectrum showed clear hydrogen emission lines, but almost zero sign of oxygen, which was exactly what they'd hoped for. That lack of oxygen, that was the precise chemical footprint they were hunting for to prove they'd found an extremely metal-poor system.
And here is the absolute smoking gun. It's not just that the overall metals are low, it's the specific ratio of them. LAP-1b shows an unusually elevated carbon-to-oxygen ratio. And it turns out that exact ratio perfectly matches the theoretical chemical yields you'd get when massive population 3 stars blow up in those pair instability supernovae we talked about earlier.
Section 5. Case closed?
Okay, so maybe the case isn't completely closed, but we definitely have the fingerprints. LAP-1b is the strongest indirect evidence we've ever had. The data tells us the metal content we're seeing was likely produced by just 1 or 2 pair instability supernovae from giants in that 150 to 260 solar mass range. It's a beautiful validation of the theories. But you know astronomers, right? They're perfectionists. They still want to catch a living population 3 star in the act.
Which actually brings us right back to our own galactic backyard. Our models suggest that if any lower mass first stars somehow managed to form, maybe they got violently ejected from their birth clusters by gravity, they could theoretically have long enough lifespans to still be burning right now. They could be hiding out in the Milky Way's stellar halo as we speak. We just have to figure out how to see past their acquired dusk disguises.
As we keep pushing the James Webb Space Telescope and future observatories to the absolute edge of space and time, it leaves us with this incredibly tantalizing thought. Is the light from the universe's very first stars, those ancient primordial giants, still out there, traveling through the dark expanses of space, just waiting to finally wash over our lenses? It is the ultimate cosmic search, and we are closer than ever to finally meeting our stellar ancestors.